We're happy to have for our first presenter, Dr. Barry Goodell from right here from campus from the Department of Microbiology. And his expertise is with bio-based and wood materials, and he's published over 130 journal articles. His list of patents, grants, and awards are, I got to tell you, they're way too numerous to mention. If I did them all, we'd use up our time slot. So his research has focused on and is focusing on woody biomass decay and biomass conversion to bio-based products and platform chemicals, biocatalytic chemistries related to bioconversion applications, and catalytic chemistries related to cryptococcal neuropathology, which I'm not sure at all what that is. But today, Dr. Goodell will speak about the problems of decay in our wooden structures, which is a multi-billion-dollar problem, and he'll be addressing causation, detection, protection, and remediation. So join me in welcoming Dr. Goodell.
Great to be here. Seeing the title there. For those of you who are doing various things that require it, there are some learning objectives that I'm sure Alex has provided. So we want to talk a little bit at an introductory level of what fungi are. I'm sure most of you have some familiarity with fungi and wood decay. And I can tell from the looks on your faces, you're all really excited about rotten wood. So we'll just expand on that a little bit more. You want to recognize, or from this talk, hopefully you will be able to recognize a little bit more than you may already know about how wood decay is established, how it can be detected, and then some real important issues, which we don't have a lot of time to cover, but we'll do what we can on identifying design issues that cause problems in the promotion of decay, particularly in coniferous species, which is what most of our wood structural material is, conifers or softwoods. And then we'll spend a little bit of time about wood protection and also remediation systems for protecting wood against decay, but also if decay starts, what do we do about that and how do we go in and protect it after the fact, so to speak. So we'll start off a little bit with information about what fungi are. And this is a whole long list of stuff that I talk about when I teach a course, which maybe eventually the university will approve, maybe they won't approve it, I don't know. It seems to take a long time to get through approval processes. Today we're not covering that. This is stuff at the bottom, which is the fungal decay, and even that we're not covering all of the fungal organisms that damage wood materials. We're going to focus mainly on decay, maybe a little bit about soft rot. These alone cause billions of dollars of damage a year, so not just in general. They're huge damagers of woody materials that cost us a lot. You often hear about termites or carpenter ants and some of the catastrophic damage they may cause, but just dollar figures alone, decay fungi are the ones that really cause the most damage. So we'll focus on them. And where are the fungi in the tree of life? Well, simplistically, they're really not all that far away from us. Okay? And some medical people talk about how difficult it is to get rid of a fungal infection. And some people, at least in the medical area, feel that it's very difficult to get rid of fungal infections as opposed to some bacterial infections, simply because the fungi are so closely related to us in the broad spectrum of the tree of life right here. And Carl mentioned this work with cryptococcus and neuropathology and that sort of thing. One of the reasons I've relatively recently, not switched over, but kind of developed a branch into studying neuropathology is because one of the fungi that is very, very, very closely related to wood decay fungi just evolved within the last million years, which sounds like a lot, but really is a very short time span. It still lives in forest trees, in the bark of trees, and somehow has figured out how to invade human lungs, pass through the blood-brain barrier, and then into the brain. And we think it's using the same sort of system or mechanisms that decay fungi use to rot wood. So that's one of the reasons I'm interested in this relatively new development. Okay, this is also the tree of life, but it's from a paper that we put out just a year and a half ago or so. And you can see that what this is lots of different organisms and different, like you've got the eukaryotes where we fit, the archaea and the bacteria here. So all the different organisms that live on Earth. Today, we're just going to talk about this tiny little fraction that's right down there. But there's a lot of different organisms that decay wood or at least digest wood, ranging from the beaver up here. And you think, well, beavers don't really, digest wood. They chew up trees, sure. But they do actually, through symbionts, they actually get some nutrition from the wood. And that's something that's been relatively recently discovered. But there's lots of damage caused by marine borers, some different types of isopods, certainly a lot of insects that cause damage to wood, and bacteria do as well. By far the most aggressive, though, are these fungi that we'll talk about today. Okay, so what do fungi look like that decay lignocellulose? Well, wood is a combination of two or more materials, depending on how you define it. Lignin and cellulose, with cellulose being about 2/3 of wood, lignin the other third. And so we call that material lignocellulose. And these are what just a few of the several thousand wood decay fungi look like. These are the fruiting bodies. We'll show you some other pictures of fruiting bodies in a little bit. And this is decay caused by one that we will talk a lot about today, and it's very common in softwoods. So again, the structural material we use primarily in wood construction. Some of you have probably had courses from Peggy or Alex and have taken a look at wood at the microscopic level. This is an image from Will Cote from a long time ago, but it's still quite representative of woody materials. This is an undecayed piece of wood with all these fibers and fiber bundles here. Those are, if you split out 3 or 4 of those, that'd be what a sliver looks like if you got a sliver in your finger. This is a pictorial from Green and Boyer's book about what the fungi actually look like here. And they find the easiest path to move through short sections of the wood. So these are the individual wood cells that are magnified from that earlier electron micrograph. And then the spaghetti that you see in here, which we call fungal hyphae or fungal mycelium, that weaves through, and the easiest path is through these natural pits that occur in the walls of the wood cell walls. So the fungi are going to take an easy path to try to move from one spot in the wood to another, and also to infect other pieces of wood, and thereby kind of increase the infection and grow their species, if you will. And I'm not sure if I can stop this. I'll get to the computer in a second here. But what I want you to focus on is this mass of spaghetti here is twirling around. And that spaghetti is, of course, the fungal hyphae. If we stop it at the right place, I guess I can't do it. Well, that's all right. If you look carefully at the edge as it goes around, you'll see that that's a piece of wood, and what we're doing very faintly, when you look at the edge, you can see the wood cells, like there's a wood cell there that's extending down through the end of it there. So that gives you an idea of how fungi invade wood and what they would look like. But it's not these fungal hyphae that are causing the decay or the actual dissolving of the wood material. It's the stuff that these fungal hyphae secrete. So they're secreting enzymes and they're secreting a bunch of different chemicals, which actually move in to dissolve the wood. Why do they want to do that? Because wood has sugars in it. And if you can dissolve cellulose, you produce sugars. And just like us, the fungi like to eat sugars, and they can increase their biomass by doing that. So that's, in a simplistic manner, if you will, how decay occurs. How is it established, and how do structural members at least start to become decayed? How is the initiation of decay? How does it occur? Well, generally it's through fungal spores, or it can be just through broken off little bits of those fungal mycelial fragments. So things at the micron level that are floating through air, and which you're breathing right now, whether you know it or not. You can often see this stuff when you're sitting near a window looking at a shaft of light coming through. So what is all that stuff? Some of it is little bits of polyester fluff that come off of your rug or your curtains. Some of it is plant fiber. Some of it is pollen from trees and plants. It may be a bit of insect grass. But a good part of it is also fungal spores and bacterial spores, or bacteria themselves. And there are billions and billions of these, which you are breathing, and you're even breathing them right now. So it's dust, essentially. So some of that dust, as I said, is composed of a lot of other things, but some of it, if you look right there, that's a little spore of a non-decay fungus right there, but the spores of decay fungi are quite similar. So you can see that once this individual head of a fungal sporulating body is disrupted, you're going to have, in this case alone, several thousand spores that are floating around in the air. When that gets up to be in the millions and billions, then you're really sucking in quite a load. Okay? And they land everywhere. Okay? So, this is courtesy of Crack magazine, which I think disappeared probably about 12 years ago. So. Anyway, why don't we look like that? Any volunteers? Okay, you're breathing in all these spores. If they landed on you, wouldn't you expect they would germinate and grow into you, just like they do that piece of wood that we showed standing around there a little bit? Well, we have a pretty good immune system, and also we're just the wrong substrate. Okay, we don't have cellulose that can be broken down to sugars, but we do have sugars that's on our skin. So if our skin is moist, and fungi always require at least a little bit of moisture, and they require a little bit of food. So if you've got moist skin and sugar on your skin, and that moisture stays on there long enough, you will get some of these fungi to germinate. Even the wood decay fungi will germinate on your skin. So, maybe you shower every day. Good thing, okay? Because you wash those spores off, even if they germinate. What if they germinate and actually start to penetrate in? Well, that's when your immune system kicks in. And that will stop the decay fungi. It won't always stop some of the other fungi that might attack humans, like the athlete's foot fungus, or maybe like cryptococcus, which kills 600,000 people every year. I guess this is gives you some perspective of how many fungi are out there and what you would look like, I guess, if you didn't have an immune system, and if you didn't shower, right? Okay, what's needed to cause decay? Water, but not too much, and also not too little. We often talk about, how much water is necessary, and in the arcane way that we determine moisture content in the wood science or the wood products field, we know that we need to be somewhere around 30%, which is what we call the fiber saturation point. Now, if you go above 30% moisture content, you can get a fair amount of decay if a lot of other conditions are right. Interestingly, and this isn't reported in too many textbooks, it depends on what kind of wood you're talking about. So we've got a few different types of wood here, different specific gravities, and just to give you some reference, 0.31, that's about the specific gravity or the density of poplar or aspen. But you go up to 0.56, that's about the specific gravity of Douglas fir or southern pine. Oak would be up even higher than that. So if you looked at oak, its curve would be something like this, meaning you really can't get up to 100% moisture content with oak and still expect it to decay. So it's actually relatively easy to stop decay in oak if you're below 30%, because below 30%, you're going to stop decay in all wood species. And in oak, when you go up really above 80% or so, you'll pretty much stop decay from occurring. But there's quite a range here. And aspen really has the largest range. So that's one of the reasons why aspen is a fairly easy wood to decay, simply because it has such a broad range of moisture content over which it decays. And if anyone has any questions while we go through this, feel free to raise your hand. So the undergrads will be responsible for memorizing all of those terms and repeating them after the seminar. Not really, sorry. This is just to show you that these are just a small number of the several thousand wood decay fungi, not fungi in general, just wood decay fungi. And the message is that you also have to have the right temperature to cause decay. So most fungal decay stops somewhere around 50 degrees Fahrenheit, but above 120 degrees Fahrenheit, like it would be the temperature in maybe your attic today, you're not going to get decay. Will you get decay in that attic in the winter? Yeah, maybe, because it will be probably the right temperature, maybe 60 degrees or 70 degrees even. But only if it's the correct moisture content. So you have to have a leak in that attic in the roof to cause moisture to get in there, in addition to having the right temperature. And then oxygen. Yes, a very complicated graph that we are not going to go into. I just pulled this out of some old literature. The bottom line is that fungi need oxygen just like we do. Okay? But they can survive at much lower levels of oxygen than we need. The oxygen level in here right now is probably about 21%, maybe 20%, because we got a lot of people and we're all breathing and respiring. Okay, we can survive at oxygen levels down to about 16% moisture, 16% oxygen level, excuse me. The fungi will go all the way down to 1%. So what does that mean? Okay, well, this is a practical example of the Saga Wave. The Saga Wave was a container ship, still is a container ship, and it was carrying wood, in this case hemlock, from British Columbia down through the Panama Canal and ended up a little south of here in New Jersey, Camden Yards. When it arrived, one of the longshoremen went down into the hold and he passed out. Okay? They didn't know what the problem was, maybe he had a heart attack. So the first mate of the ship went down into the hold, and he also passed out. No one else was going to go down into the hold after that. And that was unfortunate. Eventually they did go down, and those men were dead. And they tried to figure out why it had occurred. And the reason it occurred, I flew down there the next day, and you think on a, a scene where a couple people had died, there'd be police paper around it or something like that. No, this is business. You got to get the ship unloaded, and you got to get the ship out there for the next container. So they were unloading it as I was down there taking a look, and what you saw was all this stuff growing on the ends of the lumber, and that's a decay fungus. And the fungi, these were very closely stacked in the hold of the ship. And the hold of the ship is very, very deep. It goes well underneath the water line, and it extends on to the length of the football fungi had sucked all the oxygen out of the hole down to a level of 1 or 2%, which they survived at quite nicely, but not enough to allow humans to survive. So those men were asphyxiated, and that was the story. So these are the sorts of things that faculty members get involved in, and get called in by Coast Guard, sometimes lawyers, that sort of thing, to solve problems that are at a practical level like this one. And based on this experience and understanding, how much oxygen fungi need, how much they consume, how much humans need, et cetera, we were able to solve a problem for them and also enact some regulations which the Coast Guard now requires is that all ships that are carrying loads of lumber, particularly if it's not dried lumber, as was the case here, must have a ventilation system in the hold so that people will get asphyxiated. Okay, so some other aspects. We want to look at these fungi that cause decay. On the left-hand side are the white rots. White rots are not so common in structural environments. They do occur, but white rots are more common in hardwoods. For the most part, in the northern hemisphere of the world, we are using coniferous species, okay, or softwoods. And white rots tend to attack hardwoods. The brown rots over here tend to attack softwoods in general. So by and large, we're going to see brown rot attack, which is this brown crumbly material right here. We say that it's checked across the grain. So you see these little lines that go across here that checking across the grain as opposed to the splits with the grain. You go back to the white rots here. This is much whiter, bleached looking. If you get it in the wet state, you can actually peel it apart, something like mozzarella cheese. Strips will just peel right off. But when it dries down, it becomes a little bit more friable or fragile. Okay? These are different types of sporophores. You're not going to see these all that often, but fungi do produce them, and you'll see a lot of them in the fall of the year growing out of the ground. What are those growing on? All the ones I'm showing you here are growing on little bits of wood that are in the soil that are out in the forest. Just another example, this is a Ganoderma species that grows on hemlock specifically. So you will see this growing on decayed hemlock logs or on hemlock wood if the wood has become wet enough. And other different types. This one, I'll show you a little better picture of it here. This one down here is one that we're very interested in because it's the most aggressive brown rot organism that's out there. This is responsible for lots of that billions of dollars of damage. And this is what it would look like on the underside. We call this a poroid surface, but all these pores, which are very much elongated here, all those pores are what are producing the spores. So that picture of the dust that I showed you, the spores would be dropping out of these elongated pores, or in other cases, different species have more kind of angular pores, or sometimes they're just round-shaped pores. So billions and billions of spores are dropping out. They then are wafted away in the wind, or some of them are carried in rainwater or rain droplets. Some of them are carried by insects, and they land on other pieces of wood. And again, if that environment is correct, with the right amount of oxygen, water, temperature, and you've got the right substrate, meaning wood, then that fungus will germinate, that spore will germinate, and you'll start growing those fungal mycelia that we showed you to infect the wood, and then it starts dissolving eventually. Okay? As I mentioned, the brown rot fungi are the ones that we're primarily interested in the structural environment. So those, given the limited time we have, those are the ones that I'll focus on in telling you just a little bit more about. Brown rot fungi attack coniferous wood species. You already know that. We're in the northern hemisphere of the world. We grow much more conifers in the northern hemisphere, in the southern hemisphere of the world. Southern hemisphere has more hardwoods, right? So we just naturally, therefore, have more brown rock fungi. In early stages of decay by brown rock, there aren't many outward signs. So I showed you that picture of brown rock before. This brown, crumbly wood checked across the grain. Wood that's in early stages of brown rock doesn't look like that. It looks just like normal wood. It may be a little bit wetted, but it doesn't really look that much different than normal wood. Okay? Then for that reason, brown rotted wood can be very dangerous because it's lost quite a bit of its structural properties. Before we get to that though, we just want to check off the boxes here. Brown and crumbly, you've already seen that checked across the grain. And the wood has that brown crumbly appearance and also is shrunken up with that checking across the grain for a couple of reasons. One is that it has lost a lot of the cellulose component. So how much cellulose is in there? Roughly about 2/3, right? The other portion of it is the lignin. Lignin actually isn't consumed. Okay? And if you read even current day textbooks, but particularly textbooks from 10 years or earlier, they will say lignin isn't attacked by brown rats. Okay? That's completely false. And we know that really just from work that's been done over the last 10 years. Lignin is extensively degraded by brown rot, except it's taken apart, depolymerized, it's then chemically modified, and then put back together. And the brown residue that's left, if you take a walk in the woods, or even probably out here, if it's had a long enough period of time to digest some of the material. The brown material that we think of soil actually is a combination of brown rotted organic material plus mineral matter in the soil. Typically maybe about 50-50% in a forest environment around here. And that lignin, or rather modified lignin, which has been extensively modified by the fungus, that will persist, and this is relatively recent information. It'll stay in the soil for hundreds of years, and some workers have even dated it now at thousands of years. It's very resistant, and if you're interested in carbon cycling in the environment, we used to think of, okay, wood decays and goes up into the environment, creates, carbon in the atmosphere, and then that can get absorbed by trees. That equation isn't quite true anymore, particularly in the northern hemisphere and in forested environments, because we know a lot of that lignin, part of the tree, is actually staying in the soil for much longer periods of time. So that carbon is sequestered for a much longer period than we had previously considered. And that too is not in a lot of different models. Okay, so let's get back to the structural environment. Mechanical property laws. So let's move away from wood for just a second. If we're thinking about non-woody materials, non-lignocellulose, and we think about concrete, with rebar, okay? What happens if somehow we can take that rebar and we've got, where's the concrete? In the foot, it's okay. And we can magically chop that rebar up. What would happen to the mechanical properties of the concrete? Okay, one question. Second question, very similar. You got a fiberglass composite. If somehow magically, or maybe not even so magically, through other forms of deterioration, you could similarly chop up those glass fibers in the fiberglass composite to turn them into maybe quarter-inch pieces rather than 3 feet long pieces. What happens to it? Well, the answer is that you get very, very rapid mechanical property loss, right? You all know that because you're familiar with steel, concrete, you're familiar with, hopefully, fiberglass composites, but our composites are certain things. Similarly, if you think about woody materials, the exact same thing is happening to what I just described there, but it's happening at the molecular level. Okay? You can think of fiberglass or rebar in concrete as being similar to cellulose. These long cellulose strands at the microscopic level are what provides the rigidity for woody materials. If you go in and you chop up that cellulose, your wood loses strength very rapidly. It loses its mechanical properties very rapidly. Okay? 70% of the mechanical properties, both MOE and MOR, are lost in very early stages of decay. So this is what I'm talking about by early stages of decay. And I cheated a little bit here, giving you a hint. I took this piece of wood, which is Douglas fir. It was already a bit wet. And when I split it open, it looked just like, just like this in this corner down here. It looked just like regular wood. I knew it had decayed, and I'd already measured the mechanical properties of it and found out that it had lost a considerable amount of MOE and MOR. Okay? But I then took it and I put it in a plastic bag and I put it in a high humidity chamber for 3 days. And that's when this fungal mycelium started growing out on the surface. So that's the hint that you have that it's in a decayed state. But if you didn't have that and you looked at it when I initially looked at it just after splitting it open, you'd say, this looks like a piece of sound wood. I bet you it's good. And not knowing that it has lost 70% of its modulus of rupture and modulus of elasticity, this is why brown rot is so dangerous. And this is why we need to be concerned about it. It's not always going to look like that brown crumbly material and be very obvious that this stuff needs to be replaced. Okay, so these are some just old figures out of the Wood Handbook. Early stages of brown rot. Actually, not the Wood Handbook. This is some of Wayne Wilcox's data from the 1970s. Okay, so this is brown rot over here in softwoods, and then down here in hardwoods. And we'll just look at a couple of columns, MOR and MOE. There's too many buttons there. And we don't need all the question marks, I guess. But you can see that you've lost about 2/3 of your MOR and MOE. And then in hardwoods, similarly, we have lost that much. In wood, that again, here's a little bit wetted, but certainly not rapidly degraded. Okay? Identifying design issues. We don't have a lot of time, so I'll just talk a little bit about these. And I'm sure you've seen horror stories before with wood. So keep in mind, this is my personal horror story. Not so horrible, perhaps. This is my house in Amherst. We bought this a little over a year ago. It's a 1960s vintage house. This is on the back side. This is the gable end of a dormer. And so this whole area here, what's the problem? You can see that the clapboards have been installed right up to the shingles of the roof. And this sometimes happens if, it's an older home, the roof goes and you got to replace it so you don't actually take the shingles off. You just put new layers of shingles on top, right? Sometimes you get up to as many as 3 layers, and that will cover the clapboards. Well, I'd be okay if that was what happened in this house, but it wasn't. These are actually new clapboards, and some contractor came in and put in a new roof long before we had the house, probably about 5 years ago. And they also put clapboards in, and they didn't leave a space right here so that you can see the flashing. And that means water is going to come down here, it's going to wick into the ends of the clapboards, and it's going to decay. So, 5 years old, maybe, I'm not sure, and we already have to replace the clapboards. Terrible. You need to avoid that. That's not so much a design issue, but it's certainly something that contractors should be thinking of. And if you are designing something, make sure that you point out features like that so that they don't become further problems down the line. There's other issues in our environment. There are ways to design. One nice way is to have an overhang on the roof. A little bit of an overhang, having no overhang at all. It just means that your clappers are going to get wet and weathered. And if you're working with wood, there's no excuse for that. You ought to have a little bit of an overhang, and those clappers can last for 100 years easily if you do it correctly. Okay? You can't see the gutter down here, but there's no gutter kick-out flashing, which is needed to deflect water so it goes away from the house rather than back onto the cut. So most of this is practical, common sense stuff, but you need to be aware of it. Flashing, I just mentioned the flashing issue. This is another flashing issue. Different types of flashing. Penetrations are the big issues, primarily with all structures. They seem to come up as the biggest problem that I see in lawsuits that I become an expert witness in. Okay, we have structures that look like this. How did that happen? You have to go back and use your forensic abilities to try to figure out how did water get in. And 99% of the time it's because someone installed flashing upside down. Okay, so that it's channeling water into the structure, not down. You all know water follows gravity most of the time. There are some times where you can get particularly wind-blown rain that will even blow upward that you have to be careful of, but that's not the situation here. It was just improperly installed flash. Okay. Here we go. If you've got rain and meltwater and they're moving down a house or whatever structure you have, and you've installed flashing incorrectly, then it's going to get behind that and it's going to cause problems, at least similar to what we just saw previously. So decay is a problem. Decay causes issues that amount to thousands of dollars to repair. They're normally not the catastrophic type of issues that we see, like with something like World Trade Towers, terrorism type of disasters. However, we're building these structures taller and taller. And I know Alex and Peggy are cringing right now. Let me preface this by telling you I'm a big supporter of tall wood structures. Okay, but we need to do it right. I'm the former president of the Forest Products Society. I've been on the executive board of the Society of Wood Science and Technology, a couple of times. I support wood and want to see wood used in many different and good ways. But I've also been around long enough to see the horror stories and the way the industry in particular has shot itself in the foot. Okay, and we do this all the time. We think, I think I can use just a little less or do this just a little cheaper, and it will work out, and it ends up to be a disaster. And when we have big problems that result with, a new way of designing with wood, that gives a black eye to the entire industry, and it may prevent us from doing something that has a bright future. So we may be able to build tall structures, but if one of these structures gets in the news for having severe deterioration, then other industries are going to be, touting that, and we'll be back to steel and concrete rather than tall wood structure, which is fine. But I would like to see, a sustainable future with wood materials being used. So what do we have to worry about with these things? Lots of different stuff. If you've got flat surfaces, balconies that collect water, some of you may be architects in here. Please think about that. I get involved in a lot of lawsuits as an expert witness. And, the lawyers say, what's the problem here? And I go in, well, they've just protected this balcony with a geomembrane, a thin surface of water impermeable material. And the owner of the apartment or the tenant came in and they put a planter up against it and they drilled holes through it, okay? So immediately, you've got water penetrating this geomembrane, which the architect says was going to last 100 years. And it won't, because membranes are too easy to penetrate and rupture. And if it's not the homeowner coming in, it's some seal that ruptured, or flashing, or a sealant that failed in advance of its time. So you can't trust those, and you have to design with other things in mind. This is an example of what happens in balcony situations when you just rely on a membrane to protect. The other aspect of this is don't use southwestern architectural design in a northeast environment. So don't use flat roofs, exposed wood. As I've said before, rain is going to fall up. Rain is going to fall sideways. And it does. All you have to do is get a 30-mile-an-hour wind, and easily you can get rain, wind channeling rain upwards. So don't design using wood where a single membrane on a flat surface is protecting wood for the life of the structure. Membranes are guaranteed to rupture, and it's a disaster waiting to happen if you do it that way. Okay, I'll get off the soapbox at least a little bit. You need to recognize that it takes wood a long time to get wet, many months, but it can take even longer for wood to dry out. And that it's going to be many months to wet and then many years to dry out. You can easily get severe advanced degradation in, sorry about that, advanced deterioration in about a 3-year period in most temperate environments of the U.S. and Canada. This is advanced decay, that's advanced decay. The outside of this timber right here, look, you can't see it really, but it looks perfectly sound. Water penetrated through this check and through other surface checks to get into the interior and cause that often. The advanced decay still should be somewhat obvious. It's this area here that we need to be concerned about too, which has the incipient decay. Incipient brown rock decay is a problem, as we've already discussed. Detection of decay, and we'll go quickly through this. And when I lecture on this stuff, I usually stretch this out into at least a couple of periods, but sounding and boring. Sounding and boring is a typical term used in industry. Sounding is simply rapping on your piece of wood with a hammer. And if it sounds dull, or like this, it would sound pretty hollow, then you know there's a problem. So you go in and you bore in with a drill. And drilling is very important. You just don't drill and then fall asleep. You got to drill in, maybe at an angle, and you have to feel the wood as you go in with the drill. Did it start off kind of feeling like sound wood and then for some reason become soft? Okay, when you're drilling, do you just drill in, or do you drill in and pull out the bit every few inches so you can look at the shavings? You need to look at the shavings. You need to grab the shavings, smell them. Do they smell like decay? Do they smell like they've got a little acetic acid in them or something? That's an indication of bacteria in there. Okay? Sounding and boring is a pretty crude way of doing detection, but oftentimes it's all you need, particularly when you're doing an inspection of structure. Sometimes it's always very important to have a moisture meter with you to go in and do moisture readings. If you've got wet wood, you have a problem. You don't have to figure out, gee, is this incipient decay or is it getting to the stage where it might be advanced decay? You have wet wood. It's a problem, okay? So you need to protect it, and you need to probably even remove that. Certainly need to remove the water. Other types of detection systems, there are mechanical and sonic detection systems. My experience in general is that these are great in the laboratory, and they're also great sometimes in the build, where you've got the same dimension material being produced one after another. But if you get into a structural environment where you've got different sizes, different shaped material, you've got different fasteners, things like stress wave timers in particular don't provide the accuracy that's needed, and even attenuation of sonic waves that move through wood aren't good. There's just too many variables, even in sound of wood, that come into play. Pilodyne meters, this is a pilodyne right here. This is a little better view of it. All it is a little machine that's got a spring in it with a needle that pokes out, and you put it up against your wood and spring the pin out of it. And if it penetrates, you've got lower density wood, so it might mean you've got decay. These things are fine, but you can pretty much do the same thing with a sharpened screwdriver in peeling, if you've got a good touch for that and you've practiced a little bit, perhaps. And then you get to some fancier methods, which, you know, I don't know how many publications that was, but at least a few of them are in this sort of stuff. And they're great for academic purposes, and if you're in a lawsuit or something like that. But for practical purposes, you know, we don't need mostly, for the most part, we don't need to do culturing of pores to see what fungi grow out of them. And we don't need to do more modern techniques like polymerase chain reaction, although they do have their uses. One that I will mention, I think it's kind of cute, is this one with the electronic noses. These are the non-electronic noses right here, and dogs are actually quite effective at smelling out decay and also smelling out termites. They tend to get habituated a little bit, so after a couple hours they get tired out and aren't as effective. And they are developing and have developed things like small chromatographs, gas chromatographs, which can sniff out some of the volatiles that are produced by decay fungi and through various combinations of fuzzy logic statistics. You can analyze and smell the air, there's decay. So those are some things that are coming down the line. For specific cases where you may need to do more than assess that, you know, we have structural failure here. Okay. Protection systems. And we'll try to cover this in 5 minutes so we can get you out of here. This is a relatively new book. If you want more information, there's lots of authors that have contributed to this. We have a series of other older books too on the same sort of thing. The bottom line here, if you want a non-chemical method to protect wood, just keep wood dry. Okay? Don't let wood get wet. Don't expose it to water, and you'll be fine. Wood will last for thousands of years if you don't expose it to water. There's one non-chemical treatment that I thought I would mention because it's starting to come online, and these are thermal treatments. There's a little bit of confusion in the terminology because the Plant Protection Service, APHIS, also uses this term, thermally treated wood, but that's a heat sterilization process when you're doing import and export. The industry has tended to, call this now a thermally modified wood as the non-chemical protection. Has anyone seen any of this or bought any of this? Yeah, it's very common in Europe. And we do have a couple of plants that are making it now. You should be able to buy it, but I haven't seen it in any of the big boxes.
How is that different from dry?
Ah, okay. An excellent question. Let me see if I've got, this is the answer. Okay. So much higher temperatures than in kiln drying. And also, you're limiting oxygen. So you're not actually using like kiln to let the moisture out, the humidity out. So you've got to get very high temperatures, limited oxygen used in both of these different processes. There are a lot of them in Europe. It's quite popular in Europe, in part because Europe is much more restricted relative to the types of chemicals that we use to protect wood. Advantages are that it does a reasonably good job against protecting against wood decay fungi, these basidiomycetes, and dimensional stability is improved. But you also get increased brittleness of the wood, and that's because you get some acetic acid that's produced. And a little bit of acid at high acid at low temperatures, the wood is pretty resistant to it, but at very high temperatures, acid in wood, the wood does start to degrade.
The color change that goes on?
Absolutely. Another excellent question. Enhanced durability, dimensional stability, and good appearance. People, if you like that color change, which is this,
Yeah.
that's a piece of, this is a finish treatment system, Thermo Wood. This is the regular wood, the untreated wood, and that's the brown color. You get different shades.
So I've seen some, I haven't seen it in real life, but I've seen some ads in like JLC and stuff of, alternatives to pressure treated.
Right.
So are they is this what that is, or are they using a different chemical process that's just amberizing the wood rather than turning it into that green tint?
If it's a dark color, and they say it's a thermal process, then it's this. There are other chemical modification systems that they, like acetylation, and if we had time, I would have talked about acetylation, but the only treatment plant that did acetylation, which is, it's not quite like, but it's like taking vinegar and treating your wood with vinegar, and the chemists would laugh me out of the room by saying that, but for our purposes here, the only chemical modification plant in the country that did that is out of business now. They went out of business 2 years ago, so we no longer have that. So this is the best option that's coming down the line. And this is probably what you're going to see in the market, particularly the darker color.
Yeah, well,
it could be creosote treated too.
Yeah, it's better than the pressure treated green that we have come to know a lot.
Well, there is still some of that around. These are just, this one is a company in New Hampshire that's producing it. Otherwise, I wouldn't do commercial advertisement for them, but they're close by. The last thing I was going to cover, and we don't really have time, but chemical protection systems and creosote, pentachlorophenol, and CCA. CCA is the old green stuff, and the ACQs, which I'll talk about in the next slide actually, is the newer green stuff. But these, we used to call these the big three for preservatives. And a lot of people, well, those are the old preservatives. We now have newer ones. But these are still very widely used. They're just not available to the homeowner. So they're not available at Home Depot and Lowe's for everybody to buy. But if you walk down the street and look at a utility pole, it's treated with one of these three. So if you see a pole that's marked at SPP, it stands for Southern Pine Penta. So pentachlorophenol is what it would be treated with. It's green colored, it's treated with CCA. In those commodity products, like poles, pilings, rail ties, foundation timbers, etc., guardrails, posts, those sort of things, those can all still be treated with these things. CCA is the chromated copper arsenate, and it was banned some 12 years ago. But it wasn't really banned. We think of it as a ban, but it's still being allowed to be used for commercial applications. And they're very good chemicals, and they do a good job, except if you don't know how to use them. And there are a number of people that don't know how to use them. And I was going to say, maybe I should end here. There are newer chemicals, and if you go to the box stores or any retail lumberyard, you will be buying some of these new copper-based chemicals. But whether you're designing wood products, a lot of designers think that the design stops with the creation of the form of the structure, or maybe if we're on the research side, we're designing by doing we figured out a new adhesive to laminate beams together, or we found a new fastener to fasten wood together specification of treatment is part of the design process. So if you are doing any of those things and not thinking to the end where, gee, am I designing an exterior use product or a product that would get used in a situation where it may get wet at all? If you are not thinking that my adhesive is going to have to be compatible with something that protects the wood, my fastener is going to have to be compatible with something to protect the wood. And I've been called in cases where, you know, research has been gone on for 5 or 10 years, and they finally thought of a preservative treatment or the way to protect the wood at the end. And, you know, we've got 2 months before the product goes live or something like that. How are we going to protect it? And I have to say, there's no way that you can protect this, not with anything currently legal. And that's a terrible thing to have to say. So I really encourage all of you, whether you're going to look at any of these chemicals, et cetera, down the line, including borax, which is a very interesting chemical. If you're going to design anything, think about what you're going to treat with, and ask other people that may have some knowledge of those if you don't have background in that.
Well, I'd really like to thank Dr. Goodell for a talk that was really a terrific blend of science and practicality.